There are objects in the universe that seem almost impossible, so strange that, at first glance, they feel more like an idea from science fiction than something real. One of these objects is a pulsar, a celestial body that sends rhythmic signals into space with such precision that it seems as if some giant mechanism or perfect clock were operating in the depths of the cosmos. When pulsars were first discovered, their signals were so regular that some scientists seriously wondered whether they might be artificial in origin. The radio pulses arrived with almost perfect periodicity. Natural processes usually seem far more chaotic. But it soon became clear that what they were seeing was not the work of an extraterrestrial civilization, but one of the most astonishing outcomes of stellar evolution. For a pulsar to appear, a massive star must first die. While such a star is alive, thermonuclear reactions take place inside it. But one day the fuel runs out, the internal pressure weakens, and gravity wins. The star's outer layers may explode as a supernova, while the central core undergoes a catastrophic collapse. If the mass of that core is not great enough to form a black hole, what remains is a neutron star. This is one of the densest objects in the universe. Imagine a mass comparable to that of the Sun compressed into something the size of a large city. The matter in such a star is so dense that our usual understanding of matter almost stops working. A teaspoon of neutron star material on Earth would weigh an unimaginable amount. But why does a neutron star become a pulsar? The reason is that the original star was already rotating before the collapse. When its size suddenly shrinks, its rate of rotation increases, much like a figure skater spins faster when pulling in their arms. A huge star contracts into a tiny, ultra-dense object and begins rotating at tremendous speed, sometimes dozens or even hundreds of times per second. At the same time, the neutron star retains and amplifies an immensely powerful magnetic field. Narrow beams of radiation then emerge from its magnetic poles. These beams do not necessarily align with the axis of rotation. So as the star spins, its beams sweep out circles in space. If one of those beams regularly passes across Earth, we detect a series of pulses. Hence the name, pulsar. So a pulsar does not literally blink. It simply rotates and periodically points its beam toward us, like a cosmic lighthouse. That is why the signals arrive so rhythmically. They are not chaotic flashes, but the result of strict geometry and extraordinarily stable rotation. Some pulsars are so precise that they can be compared to the best atomic clocks. Their rhythm helps astronomers measure time, test physical theories, and study the properties of spacetime. From the slightest deviations in their signals, scientists can determine whether a neighboring star is affecting the pulsar, whether it is losing energy, or whether it is moving in a system with another object. Pulsars turned out to be especially important for science because they allow researchers to investigate extreme conditions that cannot be created on Earth. Ultradense matter, enormous magnetic fields, intense gravity, and colossal rotation speeds make them natural laboratories of fundamental physics. There are even more exotic cases. Some pulsars belong to binary systems in orbit alongside other stars or neutron stars. The study of such systems helped confirm the existence of gravitational waves long before they were directly detected. Scientists observed how the orbits of these objects gradually changed in exactly the way predicted by the theory of relativity. What is especially beautiful about the story of pulsars is that they unite catastrophe and order. Their birth is linked to the death of a giant star, to a supernova explosion, to the monstrous collapse of matter. Yet the result of that chaos is an object of astonishing regularity. It is as if, after a grand destruction, the universe creates a perfect rhythm. You can imagine a pulsar as the remnant of a massive star that did not vanish without a trace, but transformed into an ultradense heart that continues to speak to the cosmos in short, precise impulses. Each such pulse is a reminder that the death of a star can give rise to a new object no less extraordinary. When astronomers listen to pulsar signals, they are, in essence, listening to the ticking of the universe. Not metaphorically, but almost literally. Somewhere far away, a tiny, dense remnant of a dead star is spinning and sending its rhythmic message into the darkness with inhuman precision. And perhaps this is where the special beauty of science lies. It can find a strict law where at first we see only a miracle.